Hi and Assalamualaikum. My name is Yohana Safitri. So today I would like to present our project, which is Laboratory Equipment Power Control System. Let's proceed to project background. So in most engineering lab, the core asset is heavy equipment, which is power supply, transformer, and measuring instrument. So the main issue here is the manual vulnerability. So right now, this lab rely heavily on human to monitor everything manually. So when the system is manually, so it creates a major gap. So when delay response, human error can easily to lead unsafe operating condition. So next is important of laboratory safety. So we have three main points, which is safety and protection and reliability. So for safety, our first goal is want to stop the electrical shock and fire hazard. So ensuring to safe working environment for both, which is for student and technician. So next is protection. So for protection, we need to safeguard high end to protect our sensitive equipment lab, which is oscilloscope and power supply to make sure no damage due to electrical fault. And the last one is reliability. So reliability is we need to make sure all lab experiment can run smoothly and without any damage because of overload. And then next is problem statement. We also have three main points. First is manual failure. Is we too depend on human supervision. So it will cause for leaks and delay response. And next is undetected fault and critical issue like electrical overload, overheating, and improper use cannot be detected directly and instantly in real time. And next is high risk and cost. Then next is problem.
Hello, my name is Nur Muhammad Hazim bin Ibrahim. Today I will present to you about current system limitation. The first one is lack of auto detection. The system cannot detect overloads or overheating by itself. If a fault happens, there is no immediate action to stop it. Second, manual monitoring. Because we rely too much on humans to check everything, it is very easy to make mistakes or miss critical errors. And the third one is safety and damage risk. Without any active protection, the equipment is always exposed to high overcurrent. This causes system damage and unsafe condition for the users.
Hi, my name is Nurhaitin bin Muhammad. So I would like to present about system operation. So there are three types of system operation. System operation condition, which is one is normal operation condition. Second is overload condition, and third is high temperature condition. So first of all, we go through normal operation condition, which is normal operation condition will occur when power is on and there are no improper condition that any sensor will sense, which is temperature sensor, overload sensor, and door is closed. Second is overload condition. Overload condition occur when there are two types, which is machine is still powered on and second is machine powered off. Where machine powered on, overload sensor sense improper condition, which is overload power or any leakage current. So the machine will automatically shut down. And second, when the machine is still off, but the overload sensor sense improper overloading current or linkage current, they also alarm will turn on. Okay, the third condition whereby high temperature condition where occurs when there are two types, also two types, when the machine is on and the machine is powered off. So when the machine is powered on, there are temperature sensors sense any improper temperature that may cause any bad things happen later on. So the machine will go off right after temperature sensor sense any improper condition. And second, if the machine is still off, if temperature sensor sense any improper condition, when it goes off, it still alarm will turn on immediately.
So for the input and output, we got 4 for input and 2 for output, which for input, we got A, B, C, and D. A means main power, while B for temperature sensor, C for door sensor, and D for overload sensor. And for output, we got 2, which Y1 and Y2. Y1 is equipment power off, and Y2 is alarm on.
So after all, we're going to talk about how to construct the table based on what condition I mentioned before. So in this case, we have 4 input and 2 output. So construction of the table, we have to know how many input will occur. So to know how to occur, we need to times 2 to the power of n, which is how many input are available there within the circuit. So in this case, we have 4 input. So 2 to the power of 4, so we get 60. So that the truth table may have 60 input, which is 0, 0, 0, 0 until 1, 1, 1, 1, 1. So after that, in this condition, okay, as my teammates mentioned before, there are 4 input, which is A, B, C, and D, and output has 2. Y1 is actually machine off, and Y2 is actually alarm goes turn on. So as I mentioned before, there are three conditions. We have output 1 is high. So for example, we take an example for normal operation. So normal operation occur when machine will run smoothly when power is on, and there are no any improper condition, and door is closed. So as you see, equation is equation. So we need to take out any output any input that has 1 output. Okay, here we have take out all the input that has 1 output. So here, so we can assume that we can assume that 0 is actually A bar, and B and 1 is actually A. So here is 1, 0, 0, 1. Here is A, B, C, D, C. Okay, even 1, 0, 0, 1, and 1 is actually A, B is B bar, C is C bar, and D is D. Here 1 is A, B is B bar, C is C, D is D. Okay, you go you do in all the input. Here is A1, B bar, C, D. Here is A, B, C bar, D, A, B, C bar, D bar, A bar, D, A, B, C, D bar, A, B, C, D. Here for Y, you do the same thing in Y2, which is A bar, B bar, C bar, D, A, B, A bar, B, C bar, D bar, A, B, A bar, B, C bar, D. Okay, if you already have all the equation, so in SOP expression, you have to sum of product all the product that we have, which is we can write down this if that is POS equation, which is we just write down all the answer that we have plus with A, B, C bar, and D, plus with A, B, C, D, plus with A, B, C bar, D, plus with A, B, C bar, D, and finish it all here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. We have 2 more. Plus with A, B, C, D bar, plus with A, B, C, D. So here the POS equation that we, so here this POS SOP sorry, this is SOP, sum of product equation for our circuit, using KMAP to simplify all this equation, which is, let me introduce you how to use KMAP. So when we have SOP expression here, so we know that here is AB, B, A bar, A bar B, and the upper is CD, C D bar, and C bar D. So here you know that we have CD, AB, A B bar, C bar D. So you just write at KMAP table here, A bar, A, B bar, and you're looking for C bar, D, and then you write down 1 at the column. Same goes at the others. And when you have write all high output in the KMAP table, so you can see you can circle down all the input using rumus 2 to the power of 2, which is 1, 2, 6, 8, 60. So here you can see you can write down this 4. Oh, sorry, 1, 2, 4, 6, 8, 60. Okay, so you see here has 4, and here has 4, and here has 2. So when you have circled all it down, so you just see at the output AB for this circle, AB, here, AB is not changing, so we just take AB right after in front of here. Why we not take C and D? Because all in here is actually changing. It's like C, it's changing to C bar, and D is changing to D bar. So we cannot take C and D. So we just take AB because it's not changing. So second, we do expression for this for loop. So we can see B and AB and AB bar. So the part that not changing is actually A, and the upper actually C is not changing. So we take A, B, A and C. Sorry, A and C. So the last part is this one. So we take these two. So that the input that are not changing is actually A, and this one is CD. So we just take A, C bar, D. So simplify the equation using Boolean expression. So we get A in bracket B plus C bar plus D. Same goes to output Y2. We just the SOP equation here. We do the SOP equation for Y second output. SOP equation A B C D plus A bar B C bar D bar plus A bar B C bar D. Copy this. Okay, we same as Y output Y1. So just fill in the blank where A B bar here, A B bar and C bar D. A B bar and C bar D here, and the other two is here and here. So we can circle down 1, 2, 4, 6, 8. Just like before, here have 2 and here have 2. So changing part, we see if it's changing or not. So first we see here.
See A bar B is not changing, so you just take AB, and then we see the other part is C bar, D bar, and C bar D. Then the part is not changing is C bar, so you just take C. And the other circle down is A bar, B bar, and also A bar B. So the part that do not change is A, so we just take A, and then the upper one C, and also D. So we just take C bar because it's not changing.
Alright, next I will present to you about logic gate diagram circuit and the comparison between traditional and our proposed intelligent system. First of all, our circuit consists of 7 of logic gate, 2 NOT gate, 3 AND gate, and 1 OR gate for 1 2 input OR gate and 1 3 input OR gate. For switch A, it represents main power. For switch B, it represents temperature sensor. For switch C, it represents door sensor. And for switch D, it represents overload sensor. While for F1, represents machine off when the output is 1. And for F2, it represents alarm on when the output is 1. So first, the switch A and the switch C will go into the NOT logic gate, and then the output of both NOT logic gate will go into N1 logic gate. Then second, B and D will go into O1 logic gate that have 2 input, and the output of N1 and O1 that have 2 input logic gate will produce an output that will go to second AND gate, and the second AND gate will decide either the alarm will go on or off. For the second part is we'll use 3 input OR logic gate. So for 3 input OR logic gate, the switch C, B, and D will go into this 3 input OR logic gate. Then the OR logic gate will produce an output that will go into the AND logic gate alongside with the A switch. Then I will also explain to you about the output that it will be produced and the condition that required to produce the output for the alarm and the machine off. First of all, for the alarm on or F2, it has 3 conditions that will cause it to turn on. The first condition is when the overload sensor sense an overcurrent or over voltage. This will lead the output to be on, the output to be 1, and the alarm is on. While second condition is when the temperature is high. When the sensor detects a high temperature, it will produce an output of 1 and will also turn on the alarm. The third condition is when both Alright, next I will be going deep into the comparison between traditional and our proposed intelligent system. First, monitoring method. As you know, traditional monitoring method rely highly on human labor, where it managed manually by human. While for our proposed intelligent system, it is a continuous automated, where it doesn't require any manually labor and will usually produce an automatic monitoring result. While second is fault detection. For fault detection, the traditional system lack internal or predictive fault, while our proposed intelligent system have automated real-time fault detection, which can detect any fault automatically without any manually labor. Next is warning system. For traditional system, it lack the warning system to alarm the user from any hazardous environment, while our proposed intelligent system have feature of alarm buzzer an indicator LED that can alarm the user if any hazardous environment is that they're in. For the fourth one is power management. Traditional system is a managed power distributor, and also if the lab user or lab assistant forget to turn off any switch, the power will be distributed on the machine or instrument. This will cause some kind of power waste. While for our proposed system, we have intelligent power management where if it detect no user, it will turn off automatically without any manually needed.
Next, I will explain the safety level and power allocation. For safety level, the traditional system has a higher risk of electric shocks, fire hazards, and equipment damage. In contrast, the proposed intelligent system can detect faults and isolate affected circuits, making the laboratory environment much safer. For power allocation, the traditional system supplies power directly without checking the equipment status. However, the proposed intelligent systems only provides power when all the safety conditions are met. Then it can ensure safer and more efficient operation. Overall, the proposed intelligent system offers much better safety and smarter power management than the traditional system.
For now, I will present to you about the conclusion. To conclude, the objective of this project was successfully achieved. Design an intelligent laboratory equipment, management, and protection system with fault detection, power control, alarm, and cooling functions using digital logic. The proposed system improves laboratory safety, protects equipment from overload and overheating, reduces manual monitoring, and increases operational efficiency. For future improvements, IoT integration can be added for remote monitoring, together with data logging features and microcontroller-based control for more advanced functions. Overall, the system provides a safer, smarter, and more efficient solution for laboratory equipment management. So that's all from me. Thank you. For now,